Well, first of all, I would like to begin by thanking the organizer for the invitation to talk in this session. And I'm going to talk about an hematopoiesis model with an oscillatory circulation loss rate. So, the following nonlinear, non-autonomous delay differential equation was proposed by Mackie Glass. Mackie Glass, the model that Elena Braverman talked about before to describe the regularization of hematopoiesis. This is the model, the same model that Elena mentioned. Here, P denotes the density of mature blood cells circulating in the bloodstream here, and the cells are lost from the circulation at rate gamma. So the flux function F, this one, the nonlinearity of cells into the bloodstream from the stem cell compartment depends on the cell concentration at an earlier time tau. And the delay tau describes the time between the start of cellular production in the bone marrow and the release of mature cells into the circulating bloodstream. So in the real world phenomena, the environment varies with time. So it's intuitive to assume that this fact influences many biological systems, and that suggests the need of consider time-dependent parameters. And some of this paper, there are a lot of work. One, Elena mentioned a lot of work. And so a natural extension of the Mackie-Glass model, one of the natural extension of Mackie-Glass model, there are a lot of extensions, generalization of this model is this one, where we consider all parameters are time dependent. And here we add, well, the instead of only one nonlinearity, we know authors consider a summation of different nonlinearities. In this case, as M and N are always the same, independent of K of the compartment, is so the nonlinearity is always the same in each part of this summation. So here we consider M positive, and all these constants are positive, and the functions are positive and continuous. And in this case, so this function, the nonlinearity, is again the flux into the bloodstream from the cave stem cell compartment. So for each compartment, consider their own flux function. So with the different delay and the different function here, but always the same kind of nonlinearity because M and R and N are fixed. So this model, this generalization, and another ones have been intensively studied. One point is a periodical varying environment is a foundation for the theory of natural selection. So it makes sense that the constant now but varying with the time. And in these works, author assume that parameters and some of these works, parameters and delays are T-periodic functions. When they studied periodic function, assume that parameters, delays, all have the same T-periodic, the same periodic. The object of these works is studied the periodic solution. So the solution inherits the period of the parameters. So, but this assumption has the advantage of allowing the use of classical methods, as Melanie mentioned, for example, of the nonlinear analysis like the degree theory, Leggett-Williams fixed point, Schauder, well, classical methods. But from the biological point of view, a more realistic scenario is one that time-dependent parameters have different periods when authors consider different periods for the parameters, not all parameters and the solution with the same period. So the study of biological models under the almost periodic perturbations has become mandatory. Well, so this is the model again. We have a lot of works with almost periodic, where almost periodic solution of this model has been analyzed. And in all of these works, the author assumed the condition this exponent m is between 0 and 1 as fundamental for the study of this equation. In this assumption is strictly based on the fact that the techniques employed in this work cannot be applied when m is greater than 1. So we can find a lot of work with this assumption. But in different works, in all of these, authors propose the problem of extending the existing results of almost periodic solution of this model to the case m greater than 1. So our problem was assume that take the problem proposed by these authors and assume that m is greater than 1. Well, these are the constant, and other these functions are almost periodic. The delay is non-negative, and p is oscillating as Braverman in Berezansky point out in one of their work. Is really this B oscillating is for enrich the model, but in the work of Braverman and Berezansky, they point out that equation with oscillating coefficient appear in linearization of population dynamic model with seasonal fluctuation, where during some seasons the death or harvesting rates may be greater or lesser than the birth rate. So this B oscillating is the rate than where cells are lost from the circulation. So in our work, we consider all of these assumptions. And this one that is only assumption about this function oscillating. And then we put this notation for the supremum and infimum, and we assume this condition under the delays and the function R. And we also consider this constant that satisfies this inequation. All of this is for the oscillatory to take bounded the oscillating function. So B star is a bounded continuous function with positive infimum, and due to the biological interpretation of our model, we consider this initial condition for the problem. So I was talking about almost periodicity, so what almost periodicity is? Well, if we consider BC the space of continuous and bounded functions with the norm, the usual norm, and for each t, we have the following linear space, the continuous and t-periodic functions. And then we have this set of the class of periodic function. So almost periodic space is the smallest managed space satisfying this change of inclusion. But an easier definition of almost periodic function was given, for example, by Born in 1925. And he said that a function f is called almost periodic if for any epsilon, positive epsilon, there exists a number L, which the property that any interval of length L of the real line L depends on epsilon contains at least one point such that satisfies this inequation. So with this definition, we denote by APR the managed space of almost periodic real function with the usual norm, and P is this set of non-negative function, and P is a normal cone in the almost periodic space, and its interior is given by the set, this set that a function is in the interior of P if there exists an epsilon such that satisfies this inequation is satisfies. So what's the difference between the classical methods and why classical methods cannot be applied here when we are trying with almost periodicity? Well, since almost periodicity is more general than periodicity, and a central issue in the analysis relies on the fact that the involved operators are no longer compact. Due to this fact, classical methods like for example, the degree theory, super and subsolution, Leschet, William, and Schauder fixed point between, among others, cannot be extended in a direct way for the almost periodic problem. So, in view of that, other methods must be used when we are trying with almost periodic problems. So in this work, we first established the following abstract fixed point theorem, which will play an important role in SQL. In this one, this theorem in this work. And well, we consider P the cone and P circle, the interior. And well, we propose this theorem that we have the mixed monotone operator, and you assume two conditions, that there exist two functions. For clarity, the dependence of this function on T have been dropped, but all U0 and B0 are depending on T, are functions depending on T. So there exist two functions here satisfying these inequalities, and there exists another function from this interval to 0 plus infinite, such that satisfies these conditions. So if all these conditions are satisfied, the mixed monotone operator has a unique fixed point in that interval. Yeah, the interval has an order induced by the cone, the P cone. So, moreover, for any initial x0, y0 in the interval, the iterative sequences, this one and this one, converge to the fixed point when n tends to plus infinite. And we have two corollaries from this theorem that actually in the theorem I talk about the mixed monotone operator. In the first variable is non-decreasing, and in the second variable is non-increasing. So corollary one is the same as the theorem, but instead of being an operator in two variables, is in the first variable is in only one variable, and corollary one is non-increasing. It's like cut in the middle the mixed monotone operator, and from this obtain two corollaries. The first one is the with the non-decreasing operator, and the same thing, only in one variable. And the second one is with a non-increasing operator, but the thing is the same. And in all of this, and in the theorem and in these two corollaries, this kind of fixed point theorems in cones are there are a lot of them, but why the important part, or the part where doesn't function, that is not working when m is greater than 1, and that is the problem proposed by authors, that is that all in these works authors consider other fixed point theorems, but in all of them appear similar functions like that, but all of these functions has here, instead of this interval, or in all this, that interval are 0, 1, the open interval 0, 1. And when you are and you can be you need to be far away from 0 to for the theorem works in when m is greater than 1. So also I consider m and n positive constant with m greater than 1. That is the work. And define the constant b as this one. B is, if I give you a, m, and n, you can define your b, and b is greater than a if and only if a is greater than this constant that is only depending on m and n. So returning to Mackey-Glass equation, so we start our results on the existence of positive almost periodic solution of model 3, that is the generalization of Mackey-Glass equation by applying our fixed point theorems. Well, if we have these relations between n and m, and a is a constant greater than this other one, and b defined as before. So if we assume that this chain of inequality is satisfied, then the Mackey-Glass equation with m greater than 1 has a unique almost periodic solution between A and B. So on the other hand, if we have this other relation between N and M, and A is a constant that such that we have this relation between the coefficients with B defined in as before, and we assume that these inequalities are satisfied, then we have has a unique almost periodic solution such that X is greater than A. So with these corollaries, we can respond the open problem proposed by these authors, and we obtain these results. And to illustrate our theoretical results, we give some examples for each of one theorem. So we consider in this example the following model with multiple time varying delays. This one, only two compartments, one this nonlinearity and this other one where, and this is the delay, here is the delay, and where B, the oscillating function, is this one. These are the constant. This is the almost periodic function R1 and R2. And we can see that this selection of parameters and functions satisfies all the assumptions of the theorem. And if we consider, sorry, this is the example, no? And so now I need to say who are M and N. M and N. If I consider M this number and N this number in the model, and A is 4, is greater than this number, and B, so if I say who is A, I have defined B. So, well, we can see that all inequalities of the theorem are satisfied. So all assumptions of theorem 1 are satisfied. And the model has a unique almost periodic solution between 4 and 4 plus by this number. So another example for the second theorem is if we consider this M and this N greater than M. In the other example was in the other way. Well, the same, I say who is A, so I have defined B, and all the assumptions are satisfied, and so by theorem 2, we have that X is, there exists a unique almost periodic solution greater than 1.3. Or 1. So, well, that is what I want to talk about. And one thing that is a good question or future work is try to prove not only the existence of periodic solution, if not the global stability of this solution. Because if we have the global stability, if we can prove the global stability, so we can deduce from that this solution is the unique solution in this case. For example, I can see the unique solution between these two numbers, but if I can show that this solution is global, is an attractor, you can show that actually it's the only one solution in all the almost periodic space. So in the same in this case. Thanks. Well, these are I don't talk about about proofs, but all proofs are in this work. Well, these are all works that I mentioned during the talk. Well, thanks again.